Oh, good one. Good morning. How are we doing today? Awesome. Good. It's Friday. So Friday's always good, right? So, this is our announcement slide. Like I said last time, I'm probably not going to really talk through these. So when you come in, make sure you take a picture of it if you want to look at it later. But our homework due Monday nights is chapter one, and depending on how far we get today, chapter two, part one. And then on Canvas, the personal intro assignment is due the same time as your other homeworks, but that one's considered participation points. And that's under the course information module on Canvas. If you did ask a question in the anonymous box, make sure you click back on that assignment again to see my response. And that's the QR code for the GroupMe, student drop-in hours after class today, and then the mini exam coming up. Make sure I'm going to keep announcing this throughout the next week, but mini exam coming up not next Friday, but the Friday after. So 2 weeks. Here's a puppy picture for today. This is when she was like, I don't know, 4 months old or something. She was pretty big already. But that's my girl. That's Xana. Just a reminder that the Learning Lab opens on Monday, so you can go there for extra help, or just a place to work on your homework. You know, it's a nice place where you can ask the tutors for help if you have questions, or you can just, focus and have a nice dedicated place if you don't have questions. And then Eric wanted me to let you guys know that the Wednesday time and location changed. So Tuesday and Thursday are still the same, but now Wednesday is the same time as Tuesday and Thursday. Before it was a little bit later. And now Wednesday is in Held, which might be a little bit closer for most of you, especially if you live on campus. It's kind of mid-central campus. And those sessions start on Tuesday. All right, so we're just going to jump in. So last time we started looking at dimensional analysis, we described what a conversion factor was. So it's to solve problems systematically. This hopefully will work for any problem throughout the semester, but so it's good to get a hang of it now. So to solve problems, you want to ask yourself these questions. You don't necessarily need to every time, but it is a good system to have. So you want to know what your goal is, basically what units you're trying to get to. So the way that I'm going to show you how to solve problems in chemistry is going to be based on units. We're going to write down our units for every step, and we are going to cancel them out as we go and get to a final unit that we want to end up with. Then you want to ask yourself where you're starting, what you already know. So that is what units you're starting with, what numbers you're given. And some other things that you might know would be unit conversions. So unit conversions like the metric prefixes I told you guys to memorize. So 1,000 meters in a kilometer, or 1 times 10 to the negative 3 liters in a milliliter. Those unit conversions or conversion factors, sometimes they'll be given to you in the problem if they're not ones that I asked you to memorize. Conversion factors. And then how do you get there? How do you get from where you start to where you end? Sometimes you need to work backwards. But how do I get there? I like to think of it as filling in a puzzle. So filling in the pieces of a puzzle. Fill in the conversion factors you need. Bless you. Bless you. So for example, if we were trying to go from, I don't know, kilometers per hour to centimeters per second, we're given the kilometers per hour. We know that we want to get to centimeters per second. We're going to fill in the conversion factors we need to get in between there. So the way I like to do it is called this train track method. So does anybody, what do you want to change first? So we're not actually going to solve this, but we're going to fill in the conversion factors. So what do you want to change first? Hours to seconds or kilometers to centimeters? Kilometers to centimeters, great. So kilometers, how many meters are in a kilometer? 1,000. Or 1 times 10 to the third, yep. So I can fill in that conversion factor right here, and that shows me how to get rid of my kilometers. It didn't get me to centimeters yet, but that's okay. I think it's more useful to go to the standard unit, meters, than to go right to centimeters. So that would cancel out your kilometers, because if you have kilometers on top and kilometers on the bottom, km over km, they cancel out. So when we do this train track method, what we're going to do at the end would be to multiply across the top, multiply everything across the top, and then divide by any numbers that are not 1 on the bottom. So does anybody know how many meters are in a centimeter or centimeters are in a meter? How many centimeters in a meter? 100. Okay, so you can do it that way. Or if you memorize the prefixes, you can remember that 1 centimeter is equal to 1 times 10 to the negative 2 meters. That centi is basically 1/100th. So those two things mean the same thing. There's 100 centimeters in a meter, or there's 1 times 10 to the negative 2 meters in 1 centimeter. Either one would work for you. And that gets you to your centimeters. So you can check it off. That's what you wanted to get to there. Now, if you wanted to do the hours, should we go right from hours to seconds, or do you think we want to go to minutes in between? Probably minutes in between. It's easier to remember how many minutes are in an hour than how many seconds are in an hour. So because hours is on the bottom now, where do you think I want hours in my conversion factor? The top to cancel it out. So 1 hour is how many minutes? 60. Good. And then I didn't get to seconds yet, so we're going to do it one more time. 1 minute up here, so minutes cancel out, and 60 seconds down here. So now every unit canceled out except the ones we wanted, centimeters over seconds. So that's how you want to do these unit conversion problems. Think about where you're starting, where you want to end up, and fill in the conversion factors you need in between. If you don't know which conversion factor you need first, maybe you know which one goes along with your last unit. Maybe you know how to get somewhere, start somewhere, and work backwards. So this train track method is going to work for us throughout the semester. We can use this for unit conversion now. We're going to use it for stoichiometry in chapter 3, and we're going to use it for thermodynamics and things like that back in chapter 6, I think. Any questions about that kind of setup? So if you were solving this problem, say it was 5 kilometers per hour. When you plug it into your calculator, you do 5 times 1,000 times 100, and then divide by 60, divide by 60. So there's 2 ways to do it. You could do divide by 60, or you can do divide by parentheses, 60 times 60. If you don't use the parentheses and you multiply by 60, it won't work based on your order of operations. So there's few ways that you can do it, but you want to make sure you are not multiplying by this 60 by accident, because it's in the bottom. Okay, so does anybody here like Star Wars? Yeah, some people love Star Wars. Good, wonderful. So this is a very exciting Star Wars example. No. Hopefully it makes dimensional analysis unit conversion a little less painful when it's something fun. I don't know. But the quote from Star Wars was that the Millennium Falcon made the Kessel Run in less than 12 parsecs. So 12 parsecs is the unit we're starting with. And there's a bunch of conversion factors in my sentence here, but how far is 12 parsecs in meters? So we want to go from 12 parsecs and end up with meters, or M. Just call it M for meters. So do you see a conversion factor in that sentence that relates parsecs to something else? Parsecs to light years. And if I want to cancel out parsecs, should I put parsecs on the top or the bottom? The bottom. 3.26 light years is 1 parsec. Okay, do I have a conversion factor that relates light years to something else? Light years to miles. So 1 light year can go on the bottom so that those will cancel out. And 5.88 times 10 to the 12 miles goes on top. So now we have effectively converted 12 parsecs to miles. We're not all the way to meters yet. We need one more step. So 1 mile is equal to 1,600 meters. So we can put 1 mile down here and 1,600 with the little dot after it. The 1,600 with the little dot after it tells you that the 1,600, all 4 of those are significant figures. So the little dot tells you about the significant figures. Whenever you see 1, like 1 light year or 1 mile, don't count that as 1 sig fig. It's just the way that we write it to make it easier. I would worry about the sig figs in the conversion factors or the sig figs of what you started with. So between the conversion factors and what we started with, what was the least number of sig figs? 2. What we started with only had 2. So that is going to tell us what our answer is in terms of sig figs. So if we plug it into our calculator, we're going to multiply across the top, and you divide by the bottom, but the bottom is all 1s. So if you divide anything by 1, it's not going to change. So when you plug everything into your calculator, you just multiply all those things on the top, and you're going to find that your meters, your parsecs in meters, is 3.7 times 10 to the 17 meters. Any questions about that? So that might be easier than some of the ones you saw in your homework because this is only 1 unit. When it's a unit on top and bottom, it's a little trickier. So we're going to see lots of different versions here. But any questions? Yeah, so the things to memorize were 1 kilometer is 1,000 meters, or 10 to the third. 1 centimeter is 1 times 10 to the negative 2 meters. 1 milliliter, or milli in general, 1 times 10 to the negative 3. And nano, the other one was nano. We do that one in seconds. 1 nanosecond, 1 times 10 to the negative 9 seconds. So kilo, centi, milli, and nano. Cool, okay. So I have a clicker question, which is kind of a survey for you. Somebody asked me, and I wanted to see what you guys think. Somebody once told me that I should put all my office hours in the calendar, and that's helpful for you guys to add them to your calendar. But maybe it's just clogging up your calendar. So let me know. Free clicker question. There's no right or wrong answer. And it doesn't count for points this week still, but are the student drop-in hours and the SI sessions in the Canvas calendar helpful or unnecessary, or do you have no idea what the Canvas calendar is? Go ahead and get those answers in. Give you about a minute or so to do that. So are the student drop-in hours and SI sessions in the Canvas calendar helpful or unnecessary? A for helpful, B for unnecessary, C for Canvas calendar. What's that? All right. Get those answers in. Give you another 10 seconds. 5, 4, 3, 2, 1. And we're done. Somebody didn't like my blast off, so I will use blast off sometimes, but not every time. Okay, so majority said helpful. Okay, that's good. If they're unnecessary, I don't know. But if you don't know what the Canvas calendar is, let me show you in at the end of class or in office hours, student drop-in hours. I can show you what the Canvas calendar is and how to get to it. But let's keep going. So, sample problem with compound units. So what we call compound units are like when you have one on top and one on the bottom. So if we wanted to convert 85.7 meters per second squared into centimeters per millisecond squared, some of you have already asked me about this on your homework. So you've seen the trick maybe with the squared. So the squared gives you some extra hassle, I would say. So remember, anytime you see the per, 85.7 meters per, you want to write that as over 1 second squared. So the 1 isn't there, but when you divide by 1, it goes away anyway. So that's why we don't write it. But 85.7 meters per second is the same as 85.7 meters over 1 second squared. And we want to get to centimeters per millisecond squared. So we can do the top first or the bottom first. Let's do the top first, it's easier. So there are 100 centimeters in 1 meter. Like I said, if you memorize the prefix the other way, that's okay. You'll get the same answer as long as you have the right number with the right unit. So that'll get us to our centimeters. Give it a little check mark. We got that one. Now for the second squared to millisecond squared. So 1 second is equal to, or I should say 1 millisecond is equal to 1 times 10 to the negative third seconds. If you memorize the prefixes that way, 1 millisecond, milli is times 10 to the negative third. So 1 millisecond is equal to that, but 1 millisecond squared is not equal to that squared. Instead, you want to make sure you square the whole thing. So what that does for you, you distribute your square, which means you have to distribute to the number part too. So 1 squared is just 1, and we end up with 1 millisecond squared. But 1 times 10 to the negative third squared is not 1 times 10 to the negative third. Does anyone remember what you do with those exponents? You multiply them. So that ends up being 1 times 10 to the negative 6 seconds squared. So you can do it before you put it into your conversion factor, or you can do it in your conversion factor, which would look like this. 1 times 10 to the negative third seconds over 1 millisecond. Square the whole thing. That is what you need to do. You need to make sure you don't forget to square the number part too. Any questions about that? Mm-hmm. Yes. So you could do it the other way. You could have 1 second and 1,000 milliseconds and then square that. Yep. So just make sure you square that 1,000 just like we squared the 1 times 10 to the negative third. Yep. So let's see. Any other questions on that one? So all you would do is multiply whatever you got on top. So 85.7 times 100 times 1 times 10 to the negative third squared. Or that's what this guy is. Oh. Mm-hmm. Milliseconds is smaller than seconds. Yep. Nope. So when you want to have, when you're going from a bigger unit like seconds to a smaller unit like milliseconds, you're going to end up with more milliseconds. So when you go from a smaller unit to a bigger unit, you get less. But when you go from a bigger unit to a smaller unit, you get more. So it can be hard to predict that when it comes to these compound units, though. It can be hard to predict that because we also made the meters smaller. Let's see. Okay. My computer decided it was going to die right before class, so I'll pull up the answer for us. So it should come out to 8.57 times 10 to the 9 centimeters per millisecond squared. So we actually made the top unit smaller and we made the bottom unit smaller. So our number got a lot bigger. Let me double check that. I was like, that don't look right. All right. So I was like, the process is correct. My answer in my notes, I don't know what I did, but 8.57 times 10 to the negative third. Everybody else get that? Everybody that brought a calculator? Cool. Okay, hopefully you brought a calculator because now it's your turn. So we are going to be converting picoseconds per or picometers per kiloseconds into megameters per nanosecond squared. So we need some conversions that I didn't make you memorize. So 1 picometer is 1 times 10 to the negative 12 meters. And 1 megameter is 1 times 10 to the 6, positive 6 meters. And then if you didn't memorize these yet, I'll give them to you. The kiloseconds. 1 kilosecond is going to be 1,000 seconds. And 1 nanosecond is 1 times 10 to the negative 9 seconds. And I'll help you out. I'll give you this hint right here. Make sure you square the whole conversion factor, not just the units. Make sure you square the number part too for the kilosecond squared and nanosecond squared. This is going to take a little bit. Make sure you're talking to your neighbors. Help each other out. If iClicker decides to work. Let's see. Try it again. There it goes. Okay. So talk to each other, help each other out. Eric's here. He can come around and help you. I can come around and help you. Try and get those answers in 4 minutes. I know, it's quick. But you won't have too long to do these things on the mini exam or on a real exam. And it's just powers of 10. There's nothing else to worry about in these problems. Go ahead, talk to each other, help each other out. Chemistry is collaborative, except on exams. And if you are worried about the time for clickers, spoiler alert, they're all in the notes ahead of time. You can do them before class if you want. Mhm. And this is the last math we do for today, I promise. All right. Keep talking to your neighbors, help each other out. Raise your hand if you want Eric or I to come over. All right, I'm going to put up what we're thinking so far. Keep working, but looks like we got a pretty strong majority picking answer D. So feel free to change your answer. Like I said, it's collaborative. All right, so I'm going to set it up on the board. Feel free to continue getting your answers in. Like I said, the majority is D. All right, get those answers in. Anyone else? Give you another 10 seconds. 5, 4, 3, 2, 1. Going once, twice. Sold. All right. So it is indeed answer D. So when we have picometers, we have to multiply by 10 to the negative 12 to get rid of our picometers. And then we want to go to megameters. So we want to have the 1 times 10 to the 6 meters to megameters. So meters on the bottom, megameters on the top. So that gets us to our megameters, which is what we wanted to stop with on top. And then on the bottom, we want to get to nanoseconds. So kiloseconds squared, kiloseconds is 10 to the third, but we want to square it. So it's going to be 10 to the third squared or 10 to the sixth down here. And our kiloseconds squared went away. And then our seconds squared, we're going to have seconds squared that we want to get rid of down here, but we have to square the number part too to get to our nanoseconds squared. Very good. Any questions? Okay. All right, so now we're done with math for today, I promise. We're not done with class yet, but we're done with math. So just to introduce the end of chapter 1 and the start of chapter 2, we're going to be talking about models. So molecular models are used to represent atoms and molecules in 3D on the viewable scale. So computational chemistry, what's that? That's using models, basically, using models and computers to do chemistry, not to do it in the lab. So not an option for you guys, unfortunately, at least not yet. But computational chemistry is all about using computers, as the compute part might tell you. So we use computers to predict chemical properties or reactions. And I'm going to write reactions as RXN, reaction, RXNS. That's my shorthand for throughout the semester. And if you're a computational chemist, you might model molecules like hemoglobin, really big ones. Hemoglobin is modeled here to the right, and each of those little circles, little spheres, is an atom. It's a very big molecule. It has about 9,000 atoms. And if you want to see models of some other cool molecules, there's this website, the PDB, Protein Database. They have a molecule of the month that you can check out. Hemoglobin, I don't remember when it was the molecule of the month, but probably a long time ago. But there's been some really cool ones since then. So we're going to be talking about models to represent atomic or molecular scale things. So, for example, we talked a little bit about this on the first day, solids, liquids, and gases, what they look like as molecules versus the macro scale. So solids, this is a picture of the solid on the bottom left. It's very ordered. So a definition of a solid is that it's ordered and dense. And that is how it maintains its shape and its volume. So you might have learned when you're, I don't know, much younger, that the definition of a solid is that it has a defined shape and volume. It has its defined shape and volume because it's so well ordered. It doesn't need to take on the shape of a container. It has its own order to it. Liquids are still really dense, but they are disordered. And this image actually shows you why ice melts or why ice floats in water. Because if you look at that solid, there's a lot more holes actually. There's a lot more holes in the solid for water than for the liquid because of its order. So that's not the case for most substances. Most substances, the solid has a higher density and doesn't float, but for water it does. And because it's disordered, it can flow and you can walk through it. And then a gas, gases are neither. Gases are not dense and they are not ordered. So you can walk through them. You can just move through them very easily. And they take on the shape of whatever you put them in. And they take on the volume of whatever you put them in as well, actually. So their molecular properties are what we see on the macro scale as well. So the states of matter, like we said on the previous slide, solid, dense, and ordered, has a defined shape and volume. And we would say that the atoms are tightly packed. And they don't move much. You might think they don't move at all, but they do move a little. They kind of vibrate. A liquid takes on the shape of its container, but has a defined volume. It's tightly packed, but disordered. And they move a little more, those atoms. That's why you can walk through water, not as easily as air, but you can walk through water because the molecules will move. They move a little. And then a gas, no fixed shape, no fixed volume. The atoms are widely spaced. They're really spaced out. And they actually move a lot. So the atoms are spaced out and they move around freely. And fun fact, cats are both solids and liquids. There is a actual peer-reviewed physics article that describes the properties of cats as solids and liquids, and you can see the actual article right here. But there's some cute pictures of cats taking on the shape of their container, which is what a liquid does. All right. And then the end of chapter 1 is physical versus chemical properties. So, physical versus chemical properties. We saw a little bit, or we saw physical properties on the first day, physical changes on the first day. Physical can be measured without changing the substance. Measured. So if you look at something and you see its color, that you didn't change the substance by seeing its color. If you measure its melting point or its hardness, you didn't change what it is when you measured that. And when we talk about a physical change, the physical change doesn't change the identity of the substance either. So a physical change could be melting or boiling, where the molecules start really close together and then they spread out a little bit and they spread out more, but they're still the same molecules or still the same atoms. The identity stays the same. Chemical properties, on the other hand, and chemical changes, the original substance changes. So chemical properties, the way that you measure them would change the substance. The properties describe how they react with something else. So to measure the flammability of something, you have to set it on fire. And fire, setting something on fire, combustion is a reaction. Corrosion, like the formation of rust, is a reaction. To measure how much corrosion something has, you have to react it. So a chemical change is also called a chemical reaction. So a chemical change is a chemical reaction and the identity of the substance is changed. It becomes something new. And the original substance cannot be recovered through physical means. So you can't just get it back. So the balloon that I showed on the first day, when the balloon got colder, it was a physical change because when I put it on the floor and let it warm back up, it went back to exactly what it looked like before. A chemical change is not like that. You can't just warm it up or cool it down and get back what you started with. The identity is changed unless it goes through another reaction. So what are some examples? So examples of physical changes are basically what I told you, just phase changes. We go from solid to liquid to gas or vice versa. So these at the top are physical changes. And you can see that any phase change is an example of a physical change. Another example of a physical change is when something dissolves. If you think about dissolving sugar or salt in water, you can actually get the sugar or salt back by boiling off the water. So that's why it's considered a physical change. So physical changes are phase changes or when something dissolves, or if you just like rip something in half, all physical changes. Chemical changes, I talked about the first two. Combustion, it's a reaction. All chemical changes are reactions. Corrosion, this is rust. Rust formation, it's a reaction. Bless you. Another example of a reaction is if bubbles form. So reactions come with color changes, heat changes, or when a solid or a gas forms from a reaction. So this bubbling is not boiling. It didn't come from a temperature change. This bubbling or fizzing came from a reaction, the formation of CO2. So like carbon dioxide, carbonation in a drink. So bubbling counts as a, if it's the formation of CO2, fizzing, it counts as a chemical change. So there is one pretty tricky problem on your homework, which has just a bunch of pictures of different states. And it says this state goes to that state. That's a reaction. Or is it just a physical change? So sometimes, if it's just a physical change, you're only going to see the atoms or the molecules spreading apart. They won't form new molecules. They won't combine. But if it's a chemical change, you will see single atoms combining into a diatomic molecule. Or you'll see single atoms combining into A and B, like two things put together instead of being separated. So you want to look for if it's a physical change, a chemical change, or both. So you want to look at what you started with, the individual atoms, and what they looked like, if they were close together or if they were far apart. And you want to look at what the products are, if the products are combinations of atoms or if they're still by themselves. So don't go anywhere yet. This is one of those days where I'm going to keep you till the end. So I've got a clicker question, which is just, again, not for points today, but good practice. So is this a chemical change or a physical change based on what you see? We've got diatomic blue elements, diatomic white elements, and on the right, we are making something that has blue and white in it. So is it chemical or physical? And just so you guys know, I will push back the chapter 2 part 1 homework. All the chapter 2 stuff will be due the following week. But answer this one and then you are free to go and enjoy your weekend. So is this chemical or physical? Next week, we will start to speed up, I promise. We will get through all of chapter 2 next week. Have a good weekend, everyone. If you have any questions, come see me in ILSQ.